All right, welcome everybody to the lecture on Taylor series. This is one of the most important topics of the course, and we kind of have to build all the way up to it. But Taylor series are a super powerful tool that we can use to do just so many different things in all of the sciences um, and just about everywhere Taylor series show up. Okay, so reminders, Live and Math. You've got quizzes that you should be doing on certain days of the week. Um, and then everything else you can always be working on projects, aren't password protected, homeworks, uh, reflective writing, LinkedIn assignment, resume, do all those things. And then if you have any questions about any topics or any content in the course or any aspect of how the course is graded or anything like that, feel free to email me and I'll reach out. I'll reply as quickly as I can with a what days this may fit with a 6 day old baby. Okay, so let's talk about Taylor series. So Taylor series is just the name given to a power series for a general function. Okay, so we have found power series for functions that, in one way or another related to the geometric series, which when we write out a geometric series, it simplifies to that a over 1 minus r, where a is the first term in the series and R is the common ratio. And so last time we did a lot of things where like A was X and R was like X squared, and we ended up with X over 1 minus X squared has the power series, the sum of just X to the 2n plus 1, which is pretty cool. Okay. So now, what if I want to find the power series, though, for f of x equals sine of x, centered at x equals 0? Sine of x is not related to the geometric series at all. And so trying to do what we did with geometric series and trying to manipulate a geometric series to get to something that looks like sine of x isn't really going to help us here. So we need a new strategy. And what we're going to do is we'll generalize to what's known as a Taylor series. So we're going to find the power series for f of x centered, equals sine of x centered at x equals 0. This will lead to the idea of a Taylor series, but Taylor series, again, is just a power series. Okay, so here's the idea. Geometric stuff isn't going to work, so I'm going to write, I want, if I call f of x sine of x, I want to write this as the sum from 0 to infinity of some coefficients times powers of x, right? Centered at 0, so not x minus a constant or anything. This is what I want to find. And this looks like C0 plus C1 times x plus C2 times x squared plus C3 times x cubed plus blah, 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 so on and so on and so on. Okay? And here's the idea. Just like I mentioned at the end of the last lecture, the idea with the power series is that the center is the really nice point to plug in. Okay, so what I'm going to start doing is plugging in the center of the power series. Here, this power series is centered at 0. So I'm going to plug in the center into the left, into sine of x, and into the right, into the actual power series itself. Okay, so when I plug in the center into the left, I get sine of 0. Pop quiz, what's sine of 0? Answer is 0. Okay, that gives me 0. On the right, when I plug in x equals 0, notice everything except for C0 goes away. So I know that C0, let's keep track over here of what my coefficients are. C0 is 0. Cool. Now, does that help me find C1? Can I maybe plug something else in to find C1? Well, no. I'm kind of done with what I can find from the original function. So I know that sine of x, if I write out the power series for sine of x as c0 plus c1x plus c2x squared plus c3x cubed and so on and so on and so on. I know c0 is 0, but then it seems like I'm stuck. However, notice if I take a derivative of sine of x, I get cosine of x. And by the way, right now I'm not worried about the interval of convergence or anything. Um, I'm just going to assume the interval of convergence is as nice as it needs to be for me to do what I need to do. That's a very common theme in applied mathematics. Okay, so I take the derivative on the left, I get cosine of x. When I take the derivative on the right of the power series, what do I get? Let's differentiate this stuff term by term. I get, well, the derivative of c1x is c1, the derivative with respect to x. The derivative of c2x squared is 2c2x. Derivative of c3 x cubed is 3c3x squared, and so on and so on and so on. And this is like the sum n equals 1 to infinity of n times cn times x to the n minus 1, right? Cool. And now, do you see what we can do to figure out c1? Plug in the center, right? So if I plug in the center, I get cosine of 0 on the left, which is 1. And on the right, everything with an x dies off, and I'm just left with c1. Ooh, that's pretty cool. I know C1 is 1 now. Let me scooch this over. Let's keep going. Okay. Let's do the same idea. Take a derivative, plug in the center. Okay, so I'm going to take f double prime of x, which gives me negative sine of x, which is when I take the derivative of this thing now, or this thing, I'll actually do both. I get 2c2 plus, what, 6c3x to the first plus, well, up here, the next term would be 4c4 x to the fourth plus blah, 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 right? So, sorry, 4c4 x cubed. So down here, I would get 12c4 x squared, and then so on, so on, so on, so on, right? And it's actually, in my opinion, easier to differentiate this. The only thing to remember is you need to increase the starting index by 1. So this gives me the sum n equals 2 to infinity of n times n minus 1, x to the n minus 2 times cn. Sorry about that. There we go. And again, we're going to plug in the center. When I plug in the center on the left, I get negative sine of 0, which is 0. And on the right, everything except for the constant term goes away. And so I get 2c2 equals 0. Let me put that 0 in there. And so this tells me c2 is 0. Wow, amazing. Take another derivative, and I get negative cosine of x. And on the right, I'm just going to jump straight to differentiating the power series written in summation notation. This is going to give me the sum n equals 3 to infinity of Cn times n minus 1 times n minus 2 times x to the n minus 3. Okay, and when I plug in the center, I end up with, on the left, cosine of 0. That's equal to, sorry, negative cosine of 0 gives me negative 1. And on the right, everything except for the very first term, in this case, the n equals 3 term, goes away by the same reasoning as above, right? So I'll get C3 times 3 times 2 times 1. Oh, well, another way to write that is 3 factorial. So let me write that. Okay, and so this tells me C3 is negative 1 over 3 factorial. Let's do one more. The fourth derivative of x is, well, the derivative of negative cosine of x with respect to x gets me back to sine of x. I'll differentiate the power series as well. Sum n equals 4 to infinity of Cn times n minus 1 times n minus 2 times n minus 3 times x to the n minus 4. And I'll plug in the center. I get sine of 0 equals the sum n equals 4 to infinity of, oh, well, sorry. Sine of 0 is 0. And then on the right-hand side, again, the whole reason I'm plugging in the center is because everything except for the first term, the constant term goes away. That's the n equals 4 term, just the starting index here. So I get C4 times 3 times 2 times 1, which is 4 factorial, which tells me C4 is 0, technically, over 4 factorial. And notice, we're back to the original sign of x, right? We're back to that original function that we started with. So the next derivative, when I plug in 0, I'm going to get 1 on the left. And think about what you would get on the right. You would get 5 factorial C5, right? And so on and so on and so on, right? So, sort of picking up on the pattern, let's look at the pattern. Let's go back and look here. We got C0 was technically 0 over 0 factorial, because 0 factorial is 1. C1 is 1 over 1 factorial. C2 is 0 over 2 factorial. C3 is minus 1 over 3 factorial. C4 was 0 over 5 factorial. Take a second and guess what you think C5 is going to be. Back to cosine of x. Hopefully you guessed that you would get positive 1 over 5 factorial. And so on and so on and so on. So what's the pattern? What is the pattern? C in is 0 for in even, right? Whenever I take look at even derivatives in the original function, I'm getting sine of something, and that's 0. Whenever I get sine of 0, and that's 0. The odd ones, Cn equals negative 1 to the something over n factorial for n odd, right? And this is alternating. That's why we have this negative 1. So when n is 1, we get positive 1 over 1 factorial. When n is 3, we get negative 1 over 3 factorial. When n is 5, we get positive 1 over 5 factorial. And so we have this alternating nature. When n is 7, we would get negative 1 to the, or negative 1 over 7 factorial. Sorry. So sort of an easier way to handle this is just to say, well, what does it mean for n to be odd? And what does it mean for n to be even? This tells me C sub 2n is 0. That's what it means to be an even integer, is that you can write it as 2 times n. And for an odd integer, C2n plus 1, we still have in the denominator 2n, it is the index that we're getting. But then the power on negative 1, you can actually go back and check, should be n. When n is 0, so we get C1, we had positive 1. When n is 1, so so then we're looking at C3, we get negative 1 over 3 factorial. When n is 2, so we're getting 5, we get negative 1 squared is positive 1 over 5 factorial, and so on, so on, so on. Okay, so it seems that sine of x is equal to the sum n equals 0 to infinity of negative 1 to the n over 2n plus 1 factorial. And we're only including the odd powers, right? The odd coefficients. So to say that, I'm going to write this as x to the 2n plus 1. Okay, those are the only ones we're including because all the even ones are 0. Let's go and check and see if this works out in Desmos. Sine of x, sum n equals 0 to infinity, we'll do 100, minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. Hey, those are pretty similar, and we can see that we've got pretty big interval of convergence. If I scroll out, oh wow, that's really doing a good job sticking close to the sine of x curve. Over here, we start to see it break down. But it's actually the case, we'll prove this in a second, that the radius of convergence is infinity. This converges for all x. Okay. So let's actually verify that right now by using the ratio test. Okay. The ratio test says, let's look at the limit as n goes to infinity of the n plus first term, so -1 to the n plus 1, times x to the 2n plus 1 gives me 2n plus 3 over 2n plus 3 factorial. And then divide that by -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, which is the limit as n goes to infinity. The negatives just go away, and what am I left with? X to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. So we get lots of cancellation there, everything except for an x squared up here. And then the factorials, just like we talked on the first time we talked about the ratio test, we get a lot of cancellation with that factorial as well. This is the limit as n goes to infinity of, well, x squared times 2n plus 1 factorial. 2n plus 3 factorial, that's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And so we also get cancellation there and there. So this is x squared times the limit as n goes to infinity of just 1 over 2n plus 3 times 2n plus 2. And that equals 0 no matter what x is. And 0 is less than 1. So no matter what x is, this series passes the ratio test. And so this the interval of convergence here is minus infinity to infinity. You can use this series to calculate sine of x no matter what the x value is, which is pretty cool. All right, so let's generalize what we just did. Okay, so given a function f of x with as many derivatives as we want as x equals a, the Taylor series for f centered at a is defined to be the following series. And I'm going to show you where this comes from. Is again generalizing what we just did. Is the sum n equals 0 to infinity of f nth derivative of f at a, where we take the 0th derivative of f to just be the function itself, over n factorial times x minus a to the n. Okay, that is the Taylor series for f at the center A. Okay. If A equals 0, then technically we give this a different name. We call it the Maclaurin series. Maclaurin series for f. Okay. Now, let me show you where this Taylor series formula comes from. Again, it's just generalizing what we did for sine of x. Let's say we want to write f of x in a Taylor series, the sum from 0 to infinity of Cn times x minus a to the n. Okay, let's keep track of our c's over here. This tells me f of 0 is c0 times 0 factorial, technically, right? Times 1. Cool, so this tells me c0 is f of 0 divided by, oh, sorry everybody, f of a is c0 times 0 factorial. The center here is a. Okay, so a is what makes everything die off on the right, except for the constant. So I get this. So keeping track of what we have over here, we got c0 is f of a divided by 0 factorial. Cool. F prime of x is the sum from 1 to infinity of n Cn times x minus a to the n minus 1. So f prime of a is, well, I only get the first term, 1, which is 1 factorial times C1. And so this tells me C1 is f prime of A over 1 factorial C1. Keeping track up here. I'm going to use the notation in the Taylor series formula. We're going to do two more. F double prime of x is the sum n equals 2 to infinity of n times n minus 1 times Cn times x minus a to the n minus 2. And so f double prime, and I'm going to, again, the second derivative of f at a is, again, just the constant term that we get here. Well, that's 2 factorial, 2 times 1 times C2. And so C2 is the second derivative of f at a divided by 2 factorial. And hopefully you can see, oh yeah, I'm convinced that this pattern is going to hold. Let's do one more. The third derivative of f at x is the sum n equals 3 to infinity of n times n minus 1 times n minus 2 times Cn times x minus a to the n minus 3. So that the third derivative of f at a is just the constant term, which happens when n is 3, which is 3 factorial times C3. So that C3 is the third derivative of f at a over 3 factorial. Okay, and hopefully this has convinced you looking at this list. This isn't a rigorous proof, but in my opinion, it's pretty overwhelming evidence that Cn looks like the nth derivative of f at a divided by n factorial. If you want a rigorous proof, people in discrete, this is a tailor-made. Such a good pun. A tailor-made for proof by induction. Okay, so proving that the nth coefficient in the Taylor series is the nth derivative of f at a divided by n factorial. You can very easily use induction to prove that. Okay. So this is where this formula is coming from. Okay. So this is exactly what we did up here, right? We started taking derivatives of sine of x and plugging in the center and seeing what we got. And when you do that, you're either getting 1, 0, or negative 1, right? It goes 0, 1, 0, negative 1, 0, 1, 0, negative 1, which is exactly what we see coming up here. 0 over 0 factorial, 1 over 1 factorial, 0 over 2 factorial, minus 1 over 3 factorial, so on, so on, so on. And sometimes the hardest part of the Taylor series, honestly, is once you have this, it's just recognizing the pattern to write in a simpler way. But most of the time, as long as you understand how do I convert something that's alternating like this into -1 to a certain power, then you're pretty good to go. Okay. And in fact, we have the pattern right here. You just need to know that nth derivative of f at a. All right. We can also still use what we know. So we just found the Maclaurin series for sine of x. And in fact, this is something that I would encourage you to commit to memory. Maclaurin series for sine of x, that means Taylor series centered at 0, is the sum n equals 0 to infinity of -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And by the way, from the Taylor series, we can get a lot of information like the Taylor series for sine of x only has odd powers of x, and that's why sine of x is an odd function. Okay, that's pretty cool. So we can use what we used yesterday, or in the last video rather, to get information about functions related to sine of x. For instance, cosine of x is the derivative of sine of x. So if I know the Maclaurin series for sine of x, then the Maclaurin series for cosine of x is the sum n equals 0 to infinity of -1 to the n over 2n plus 1 factorial. I took the derivative on the left. The derivative of sine of x is cosine of x. So I'll take the derivative on the right. The derivative of x to the 2n plus 1 is 2n plus 1 times x to the 2n. And notice, I can technically, if you want to leave it like this, you can. No one does. You'll also notice, Dr. Matheson, you forgot to increase the index by 1. Well, if your starting power of x is actually x to the first, because when n is 0 here, I get an x to the first, then you actually leave the bottom index as 0. You only increase that if your starting index truly corresponds to a constant term. Okay. So, do some simplification here. This is the sum n equals 0 to infinity of minus 1 to the n over 2n plus 1 times 2n factorial times 2n plus 1 times x to the 2n. Bingo, bingo. And we have our power series for cosine of x, our Maclaurin series. This is the sum n equals 0 to infinity of minus 1 to the n over 2n factorial times x to the 2n. Okay. Because we got this from the power series for sine of x, the interval of convergence, the radius of convergence is the same. And because the radius of convergence is infinite, that means that the interval of convergence is also minus infinity to infinity. So let's check this power series out. Here's cosine of x. Here's the sum n equals 0 to, again, technically infinity, but Desmos hates infinity. Minus 1 to the n over 2n factorial times x to the 2n. And there we go. They match up perfectly. So that's how, once you know the Maclaurin series for sine of x, you can find the Maclaurin series for cosine of x. So some ways that some tricks I use to help myself remember the Maclaurin series for sine of x is, sine of x is odd, so it's only going to have odd powers of x. And because of the alternating nature of sine of x, it oscillates, right? That helps me remember I need a minus 1 to the n in there. And then the over 2n plus 1 factorial simply comes from the fact that in a Taylor series, this thing, the number inside of the factorial, matches the exponent on x, right? And so that helps me remember the formula for sine of x, the Maclaurin series. All right. So everyone take a second, pause the video, and try to find the Maclaurin series. So that's the power series, the Taylor series centered at 0 for the function f of x equals e to the x. And then use that to find the Maclaurin series for f of x g of x equals e to the minus x squared. Okay. Hopefully you paused the video. For e to the x is the nicest function because if f of x is e to the x, then f prime of x is e to the x, and f double prime of x is e to the x, and so on and so on and so on. And the nth derivative of f of x is e to the x, right? So that means that the nth derivative of f at the center 0 is e to the 0, which is 1. And we can say that the Maclaurin series for e to the x is the sum from 0 to infinity. Just by definition, it's this. What I've written right now is not specific to e to the x. This is the general definition for the Maclaurin series for f of x. But now I'll plug in what is that nth derivative of f at 0? Well, it's always 1. So 1 over n factorial times x to the n. And there we go. There's our Maclaurin series. If you want to find the interval of convergence, it's this converges. The radius of convergence is infinite, so this has an interval of convergence minus infinity to infinity. So here we go. Here's e to the x, and here's the Maclaurin series, or at least the first 101 terms. x to the n over n factorial. There we go. And you might remember that I said on a certain day in the notes that the sum from 0 to infinity of 1 over n factorial is e to the first, and that comes from this Maclaurin series. Okay. Pretty cool. All right, so how do I use this to find the Maclaurin series for, for e to the minus x squared? Well, this is g of x equals e to the minus x squared. That is f of minus x squared, right? And again, remember, everything you learned about power series transfers over to Taylor series and Maclaurin series. Okay, so if I plug in minus x squared into a power series, or sorry, into the function represented by a certain power series, then I can just plug in that same thing into the power series itself. Okay, so this is the sum n equals 0 to infinity of minus x squared to the n over n factorial, right? All I've done is I've plugged in minus x squared into the Maclaurin series for e to the x. Okay. And this gives me the sum n equals 0 to infinity of minus 1 to the n times x to the 2n over n factorial. This is, so here I would say the Maclaurin series. I'm being pretty careful with my wording here, I'm being a little pedantic, but the Maclaurin series for e to the minus x squared is this sum from 0 to infinity of minus 1 to the n, x to the 2n over n factorial. Let's go compare these functions. Here's e to the minus x squared, cute little guy. And here's the sum n equals 0 to, again, technically infinity, minus 1 to the n, x to the 2n divided by n factorial. And we get the same function. Wow. And in the next lecture, I'll tell you why this is important and why this is really, really cool. Um, uh, and why this matters. So that's where we'll stop. If you have any questions, feel free to email me. And you'll get a lot of practice with Taylor series on homework for this week. So make sure you're doing the homework. There's also going to be a Taylor series quiz that you can do. So make sure you look at that once you feel comfortable and confident with Taylor and Maclaurin series. Okay. Again, if you have any questions, feel free to reach out. Thank you all for watching this video, and I'll see you guys in the next one.